hear me well. Please, if you have some problems with hearing, just raise your hand or something. I will slow down and we will solve the problem. I would like to say a good day from a hot and humid Zagreb. Here you can see the picture from our Met service in the early morning. It was clear. Now already some clouds are approaching from a southwest, and we expect some thunderstorms in the afternoon hours. Also, last days we had synoptic situation which supports some convection. It was also mainly in afternoon hours, so diurnally driven thunderstorm in unstable air mass. So let's start, and I would like you to point on the map from where you are listening this weather briefing. Okay, really from different parts of the Europe. I hope that I will cover most of the weather, but first I will start this briefing, so to say, with a little bit unusual thing. I wanted to start with some slides that refer to the weather that was last weekend, because this was the main topic in the weather world, so to say. So if you can see on air mass RGB, tropical storm Mekunu that hit Oman and Yemen on Friday night and on Saturday. I will play it again. So please, if you don't see the movie, raise your hand or put the cross. This is a quite interesting event, because the category 3 landfall is the first in the satellite era in the south-west Oman. Although the Arabian Peninsula is affected by a tropical cyclone every 1 to 2 years, a tropical cyclone landfall at the equivalent strength of a hurricane is rare in western Oman or eastern Yemen. On this air mass loop, you can see the air mass is warm and where the cyclone is. So over the, I must go back to this one. So where the cyclone is over here, over Arabian Sea. The green color is, so to say, light green color, and it reveals the high upper tropospheric humidity. But the dark green over the Arabic Peninsula shows the warm air mass with low upper tropospheric humidity. So also what we can see in the white color are the high-level thick clouds. I will show you also the RGB storm. It's easier with this RGB to notice the thick ice clouds with small ice particles on the top, and this may suggest the severity of the storm, because they are a result of a strong updraft, which will be see in a few seconds. But before, I wanted to say that Salalah, the city in Oman, reported 617 millimeters of rainfall in just 4 days, which is, of course, incredible amount of rainfall in a short period of time. So on this slide, you can see the cross section through the cyclone, and it shows a very strong vertical motion, and also what is quite interesting, the PV anomaly showing lowering of the tropopause almost near the surface. Of course, Mekunu weakened after entering the mainland, and but still winds gust up to 17 miles per hour were reported at Salalah airport, and the storm surge, flooding of low-lying coastal areas was reported just ahead of arrival of center of shore, and there were wave heights of 8 to 12 meters. in this part of the coast. You can see it here also. This is a forecast of ECMWF of base heights. So this was a quite, so to say, high impact weather event. You can see on the photos the damage and the amount of the rain, what caused flash floods, and as maybe you already know, lots of people reported missing, and some casualties also were reported. This was about Mekunu. I hope that this was not boring to you. And now we will skip on today's weather. And what is the marking this day in Europe is persisting blocking, excluding the far northeast Europe, where a cyclone is moving from Finland to Russia, but this is even not seen on this map. So the middle Europe and North Europe is, so to say, without any cloudiness, but the western part of the Europe and the eastern part of the Europe is covered with cloudiness. This is connected with the low pressure systems. You can see it here with the overlay of mean sea level pressure on ER image. This blocking is also nicely seen with the geopotential height at 300 hectopascal. So we have the positive anomaly placed over here in the north, and also, so to say, a ridge here in the middle Mediterranean, but we have lower geopotential heights in place over Western Europe, here one over Scandinavia that is moving retrogradely over Scotland during the day, and also one trough here situated over Turkey, and this trough was already resulting in some thunderstorms even in early morning hours. You can see it over here. And there is a small cold core placed here north of Hungary. Also, what is interesting to notice here on this map, on this image, where we have overlaid this 300 hectopascal geopotential height and isotachs at 300 hectopascal, you can see that the polar jet is really far north. Now we will move to the next image, and this is air mass RGB, where of course you're already familiar with. You can see the distribution of the main air masses. So there is a warm air mass situated here over Mediterranean, here over the east, and we can say cold but not so cold air mass situated over the western part of the Europe, and here in this high pressure field over North Europe. I would like you now to point out, with a highlighter, at least 3 areas where you can find dry descending stratospheric air, please. Okay, thank you. I've noticed that already somebody put a yellow dot on the one that is for me quite interesting today. Okay, so you find most of them. Thank you. So you're quite familiar with them. Okay. Thank you. Okay, thank you very much. Now we will overlay the PV anomaly, and most of you have chosen the right places. What I wanted to comment with you was also this nice PV anomaly over here. This was, if you remember, the small cold core placed over northern Hungary, and this PV anomaly, so to say, is also helping thunderstorms to build up already in the middle of the day. Okay, let's move on to the next slide. Here you can see the natural RGB, and it also shows that parts of the Europe that are without the cloudiness, this you can nicely see also some rivers over here, but the parts of the Europe covered with cloudiness, this western part and this eastern part, these clouds over here are also with ice crystals in turquoise color. And what was the point with this RGB I wanted to highlight also the region over, so to say, middle Mediterranean, the coast of Algeria and Tunis. You can see there are some, the dust is nicely seen in this RGB in early morning hours. So I hope that you can notice this here in this region dust. It is also can be nicely seen in dust RGB, but since the amounts of the dust are, so to say, rather small, this it is not seen in so pinkish color as we would probably expect. For the now, I would want to turn to this image. This is what the main, so to say, concern of the weather today, since there is no synoptic scale fronts over the most of the Europe, just low pressure fields. We expect storms that will be built up during the day. We saw that already some storms were building up in the early morning over the Turkey. So the total precipitable water from the 06 UTC shows the presence of the moisture, but of course it's only seen in the parts of the Europe where there was no clouds. And we see lots of moist here over the middle, in the eastern Mediterranean, here over Germany, over the Alps, the Balkans, and this is these are the parts of the Europe and that we expect that can have some convective development over day, as well as these parts that already have some cloudiness, so we already know that the moisture is present. We can also check up the product from a satellite. This is a GII-KI index, and it shows the, so to say, unstable conditions in the same region. So this is part of the Mediterranean, especially Apennine Peninsula, also parts of the Eastern Mediterranean, but also the parts of the Germany, Denmark, and Benelux countries, and here in Hungary. And if you have checked up the satellite image, the last satellite image from 12 UTC, you could see that already some storms are developing over Alpine region, also some storm here in southern England, but lots of storms already here over the Turkey, and some storms building up here in Croatia on Dinaric Alps. So with the combination of diurnal heating, orography, with mid-level short waves and convergence zones, thunderstorms will form in the afternoon. And the main threat, since all these storms will be slow moving, will be, so to say, big amounts of rain in a short period of time. Already yesterday and the day before, we have seen, probably you have already seen flash floods reports from, especially from Germany. Okay, this is all from me now, and I will now leave the floor to Marko, who has prepared very interesting slides for you. And if you will have any questions about this part of the presentation, I can answer them. Thank you.
Okay, hello, so we are back. So let's continue with the weather briefing about some specific areas, namely Croatian coast, Iceland and Eastern Europe, as it is said just here. So I will talk about some interesting features I found on satellite images the last days and weeks. For starters, I would like to show you a tiny case study I made for our Facebook page, EUMeTrain's Facebook page 2 weeks ago. You can just type in facebook.com/EUMeTrain and check out our new materials and maybe some new case studies that we published, small case studies. So at the beginning, on the Croatian coastline and in the Adriatic, you could clearly see signs of convection starting from early morning hours on 17 May 2018 from 4:30 to, let's say, 6:30. And now I'm showing you some images from that period. And if you look at these images chronologically, you can see how the freshly forming cells also suck the moisture from the lower levels close to the ground. And you can probably recognize from the shape of this line that the convection was supported and created by convergence of wind. We'll come to that a bit later, but for now, you will believe me on that. So if we look at this QT diagram from that night at 00 UTC from Zadar, Zadar is around here. We can see that the lower levels of the troposphere were moist, up to about 850 hectopascal. So we have, with that, one ingredient needed for convection. Cape, on the other hand, was quite low, around 30 joules per kilogram, as you can see from this QT diagram. But the environment could have changed it a little slightly in the next few hours, since the main convection has been going on from around 4 UTC to 6 UTC. So the environment could have been changed just slightly. So at least the sin would be broken. So we wouldn't have so much capping. That is actually balanced with cape in this case. So basically, we have instability present. We have moisture. We have shear around 5 meters per second. This was, I read this from this diagram, but maybe it's not the most accurate way to measure it, but it's around 5 meters per second. And as the environment changed, maybe even more in the morning. And the last thing we need is lift, the trigger that would trigger this convection that was going on in the morning. So the answer for that is the convergence of the wind. On this map on the left side, you can see the wind barbs going like this in the middle of the sea and colliding in this convergence line, and thus creating at the beginning small cells that later grew into real big convective cells, and we will talk about the consequences of these cells a bit later. But there is clear evidence of the trigger for this convective storm, so the convergence of the wind in the lower levels. And on the right side, we can see on this image that the cape, this is modeled cape, of course, the cape rose just slightly to around 200 joules per kilogram. Maybe there was more, maybe there was less. This is modeled, of course, and we don't have such frequent data, neither spatially, not temporally. And you can see the signature from these convective cells as their cold cloud tops have, their temperatures have fallen down to around 215, 210 kelvins. So basically what happened in the end? The storm produced some lightning, of course, it produced some rain. It rained on the islands that you can see here. But also the storm produced 6 water spouts. I'm sorry, it is wrongly written here, 2 water spouts, but in total there were 6 water spouts formed off coast of island Susak, that is around, let's say, here. So in the middle of this convective line, you can see some nice images taken from the island. And yes, that was from the time interval from 5 UTC to around 540 UTC, and each of them lasted around 10 minutes. So this was this small case I wanted to show you. We can now continue to the other things. We have 2 more things to cover. Yeah, sorry. I just wanted to show you the event that transpired in the southern Adriatic when a convergence line and a downdraft from this cell, also created by the convergence line, when they collided. So you can track the images. You can see how the downdraft collides with the convergence line, and at this point a small cell develops, although the cell wasn't very strong, and it disappeared quite soon after. So okay, that would be all for this short case study. I would like to go to the other slide. I have a question for you. So please look at this image and select what do you see on it. Please use the markup and select one of the, or maybe more of these options in the lower right corner. Okay, I see everybody is pointing to the obvious one. Somebody also pointed to a bit less obvious one. But yes, all in all, you are right. You have chosen correctly. So basically, let me just clear this. So basically, we can see the lee cloud that is forming because of the southwesterly wind flowing over the mountains in Iceland. We have here one peak, Hvanadalshnúkur, I believe it's named. It's around 2,000 meters. So I'm not so familiar with the orography of Iceland, but I believe that the mountains there quite helped actually produce these lee clouds. We can see all these very yellowish, very bright yellow colors of the cloud that suggest that we have very small and or very cold particles. And another thing that we can see on this image actually is one thing that only one person, I think, pointed out is a formation just over and to the southwest of Iceland. And that is the super cool cloud that we will analyze just a few moments, for a few moments, I'm sorry. So yeah, basically we can see that if we switch the images, we can see the difference between this super cool cloud, actually this feature, southwest of Iceland. We can see that in the convective clouds, RGB, it is and in clouds, so nothing special with it. We cannot actually discern them from other clouds, other water clouds from in this picture. But the next topic that we will come to is this lee cloud that we were just talking about. So we can see in the convective storms RGB, the cloud was very bright. The yellow color of the cloud was very bright, and that is due to this very cold cloud top temperature, and also maybe from the very small particles that are usual and common for these Lee clouds. Also, on the other hand, regarding that water cloud that we looked at on the slide just before, we can see that its cloud tops are also quite cold, around 225 kelvins, which is very cold for a water cloud, actually. And to go to the other slide, I made some vertical cross sections of this cloud. I was interested actually if there is something maybe interesting about it, something special about it. I found some interesting actually vertical cross sections in comparison with the Bora conceptual model. As you can see, it has similar moist distributions over its vertical cross section. The wind speed on the lee side increases, as you can also see on the observations on the south side of the island. You can see the wind is around 5 to 6 meters per second, and on the north side it goes up to maybe 15, maybe more. And the omega is also quite similar to the Bora vertical cross section. We can see the descent after the pass of the mountains and ascent of the air, actually the wind also after the pass of the mountain. The only difference between the Bora vertical cross section and this case is actually that there is no hydraulic jump. As we can see here, there are no breaking waves in this pattern. So this is obviously not anything similar to Bora, but maybe after some discussions with my colleagues here at the office, we maybe concluded that this is probably some kind of katabatic wind blowing over the plains and over the mountains of Iceland. So to analyze till the end the RGBs, we can see here that the red and green colors of this convective storms RGB are the highest. Blue is low because the top of the cloud is cold, and the red actually, as you can see here, it denotes the height of the cloud, so it is a rather high cloud, and the green color denotes the size, particle size, or the temperature size, the temperature of the particles in the cloud top. So basically, when you then combine the two colors, you get the yellow one that we have here. On the other hand, the feature to the southwest of Iceland, we see that all colors are almost the same. So basically, we have a rather high cloud in red. We have a rather cold cloud or particles of small size in this cloud, and we have a water cloud which is shown with blue color. Yeah, I'm sorry. I mentioned before that that the color here, that the blue here is low because the top is very cold, but this is actually for the indicator for the low water clouds. So this is obviously not a low water cloud in the convective RGB. And at the end, the natural colors, we can see here that this is obviously a water cloud because we have all the ingredients almost at the same amount, and that would be different for ice clouds because ice absorbs more of the 1.6 near infrared micrometer of this part of the spectrum. So the ice clouds here would be represented by this cyan color. So we can clearly see that this is water cloud, but here this is the indication that it is a super cooled water cloud. So something for the end. This is the last case I wanted to show you. So please take your annotating tools and mark areas with high moisture content first. Please do that first so we don't get messed up. Okay, I see some of you are going for a quite broad area, but basically what the red line and the red ellipse encircled, that's the main area that's of our concern, and that's the area with the highest moisture content right here. I'm not counting in the frontal surface, frontal zones. We don't want to do that now, but yeah, actually this, what you noted is correct. And please now again mark where do you expect some convective development in the afternoon. So only your decision will only be based on this satellite image. And actually, please, if do not take into account the frontal zone, let's take it a bit out of this picture. Okay, generally I see you got the point. You encircled a lot of correct areas. Basically, I will now erase your annotations. Yeah, sorry, I will just erase them and show you what I wanted to say. Basically, I wanted to point out this place, this area with very high moisture content. So you can see it actually from the colors on this 24-hour microphysical RGB. The color, the blue, is darker, which means that we have more moisture in it. Or if you want to look at it from another angle, you have less red. So red basically means that the air would be dry, and here we have dark blue, which is quite the opposite. And so the other question is, where do you expect convective development in the afternoon? Basically, the area is the same. I did not take into account the front line. I mean, that's quite obvious that there will be some rain, some development, but here now in the clear air, in the clear area, we can expect convection also here, where we have the highest amount of water. And we can actually verify this by switching to 12 UTC image, and basically in the same place where we noted the high moisture content, we got some convection. Now the other question I have for you is, what's actually going on here to the east over Ukraine and Russia? If you have any ideas, please write in the chat box or raise your hand so I can give you a right to speak. So anyone? We see something is different from the rest of the picture. We have one question, one answer: hot land surface, subsidence, hot and dry. Interesting. So basically, Yes, we got one answer also on the image, and yes, the last two, and yeah, some of the people are now writing. We have a very dry atmosphere, very dry troposphere actually. So most of your answers were correct. The temperature, I'm not sure at the moment. I saw some answers with the temperature, but the atmosphere, the air actually over that area is very dry. And we can actually, in this 24-hour RGB, we can actually see the rivers that are flowing there. So Volga, Don, and Dnieper, and their tributaries actually. So we can basically see all through the troposphere to the ground. And what is even more interesting on the other side, yes, here we can actually see the analysis. So the red is very low. So the 12.0 and 10.8 are almost the same, almost of the same amount. So that means it is quite dry. And with what is even more interesting, that you can also see the rivers and the surface features on air mass RGB, which I don't know, I'm maybe not that experienced, but I have never seen that. So basically you can also see the river Dnieper, the Don, and the river Volga. And here on the left side you can see the SQT diagram for Rostov-na-Donu, the city just near the river, and it's quite clear that the air above it is really, really dry. And for the end, I would just like to show you the model output for that day, and we can also see that around Ukraine and Russia, we can see that the total precipitable water is really low. So basically in some parts of Russia and Ukraine, we have only up to 6 millimeters of total precipitable water. Of course, this is model, it's not exact, but it probably represents quite well the situation. And that would be all from me. Thank you for your attention, and for all the questions that you might have, please, you may ask now. Thank you.